We will get started now. Good morning, everyone, and welcome to day 2 of this conference. This morning session, we will have 3 talks. Each of them will be 35 minutes plus 10 minutes of discussion. And we will get started with Robert Brandenberger. So the stage is yours.
Great. So first of all, I'd like to thank the organizers for inviting me to speak and for organizing this workshop. I'm quite excited to give this talk. I'll be talking about work which is very much still in progress. And it's work in collaboration with Shudo Brahma and Samuel Liberté. So to set the stage, I guess you all know that inflationary cosmology has become the current paradigm of early universe cosmology. Now, inflation is usually analyzed using an effective field theory framework. However, it has now become clear that there are fundamental conceptual problems for any effective field theory description of a rapidly expanding universe. And these are problems which are independent of string theory. It's a unitarity problem, it's an inconsistency with the second law of thermodynamics. So it's quite important things. So if you buy this, then you conclude that we need to look beyond an effective field theory description if you want to understand the whole universe. And this is where the topic of my talk comes in. I'll be trying to develop an approach starting from the BFSS, Banks, Fischler, Schenker, Susskind matrix model, an attempt to derive cosmology from it. Okay, so what is the menu for this morning? First of all, I'll try to persuade you that indeed there's a breakdown of any effective field theory analysis of an expanding universe. Then I will remind you that there are more scenarios for successful early universe cosmology than inflation. There are alternatives. And then I will remind you how one computes density perturbations and gravitational waves from thermal fluctuations. So you see parts 1, 2, and 3 are very much reminders. And then part 4 will be the actual topic of the talk, trying to extract an immersion cosmology from matrix theory. Okay, so let me turn to the problems for an effective field theory analysis of an expanding universe. So now we'll start with work that Jérôme Martin and myself did 20 years ago. And 20 years ago, we presented this space-time sketch for inflation. So the vertical axis is time, the horizontal axis is physical spatial coordinates. This space-time sketch corresponds to inflationary cosmology, inflation lasting from time t sub I to time t sub r. Okay, and there are various length scales plotted in this graph. First of all, there's the horizon, which is the forward light cone from some initial time, which I take to be close to the Big Bang. And during inflation, the horizon expands exponentially. Then the solid blue line is the Hubble radius, which is the inverse expansion rate. And this is constant during inflation. And the red line, this is a physical wavelength corresponding to fixed comoving scales. So we observe perturbations on large scales today. And the beauty of inflation is that these length scales emerge from inside of the Hubble radius at the beginning of inflation. And so therefore there is a possibility of having a locally causal structure formation mechanism. Now, as we pointed out 20 years ago, is that if inflation lasts a little bit longer than it needs to be in order for the current Hubble radius to emerge at the beginning of inflation inside the Hubble radius, then scales that we observe today start out in the trans-Planckian region of ignorance, in the region where wavelengths are smaller than the Planck length and where we know that the effective field theory analysis breaks down. So 20 years ago, we basically said that new physics must be taken into account when computing observables from inflation. However, 2 years ago, a new twist to this problem was put forward by Bedroya and Waffa in the paper which I give you the archive number. And they put forward the conjecture that in no cosmological model that is consistent with ultraviolet physics, trans-Planckian modes can ever exit the Hubble radius. So the mathematical form of the trans-Planckian censorship conjecture is contained in this equation in the box. So if you start at any early time, at any initial time p sub I with a Planck length, and you evolve the scales to any later time p sub r, then you have to remain inside of the Hubble radius. So this is a TCC conjecture. And where does this come from? I'll give you three arguments. One argument is in analogy with Penrose's cosmic censorship hypothesis. So Penrose says that singularities inside of black holes, which would give rise to non-unitarities and bad physics for observers far away from the black hole, have to be hidden by a horizon. So if you take a black hole with charge smaller than the mass, then the observer outside of the black hole is indeed shielded. However, general relativity, as an effective field theory, admits pathological solutions where the singularity is not shielded from the observer. And so Penrose says that even though the effective field theory admits pathological solutions, the full theory, the full ultraviolet physics should prohibit these pathological solutions of the effective field theory. So it says that the external observer should be shielded from the singularity and non-unitarity by the horizon. So let's translate Penrose's cosmic censorship conjecture to cosmology. So the translation scheme is position space becomes momentum space. The singularity becomes the space of trans-Planckian modes, and the black hole horizon is replaced by the Hubble horizon. And so Penrose would state that an observer measuring super Hubble horizon modes must be shielded from the trans-Planckian modes. And this is exactly the TCC. And why should we use the Hubble horizon? Well, the important point is that fluctuations only oscillate on sub-Hubble scales, and they freeze out and become squeezed states and can classicalize on super Hubble scales. And a conservative demand is to say that it is the classical region which would be insensitive to the trans-Planckian region. And everything that is on this slide, I should say, is unaffected by the preprint which appeared this morning on GRQC by a couple of authors. Okay, now the second argument for the TCC is the unitarity problem. So as pointed out by Nathan Weiss, already long time ago, and recently revived by Kotler and Strominger in this paper, if we take an effective field theory, then there's a unitarity problem. Because in an effective field theory description, we quantize each co-moving mode of a field. So the Hilbert space is a product Hilbert space of harmonic oscillator Hilbert spaces for all co-moving wave numbers. But we need an ultraviolet cutoff, and the ultraviolet cutoff has to be on physical length scales. And so to maintain a fixed ultraviolet cutoff in an expanding universe, you have to continuously create modes, and this is extreme non-unitarity. And so if we demand that the classical region be insensitive to this non-unitarity, we again get the TCC. So this is a second argument for the trans-Planckian censorship conjecture. And the third argument comes from the second law of thermodynamics. So let's consider the entanglement entropy between sub and super Hubble modes. And let's consider a phase of inflationary expansion, in which case the phase space of super Hubble modes increases. And that means that the entanglement entropy also increases. And so if we demand that the entanglement entropy density remains smaller than the post-inflationary thermal entropy density, then we get an upper bound on the duration of inflation, which again is consistent with the trans-Planckian censorship conjecture. So based on all of these arguments, I hope that you will allow me to postulate that there are problems for any effective field theory description of a rapidly expanding universe. And what does that imply for inflation? So here's my space-time sketch of inflation. So horizontal axis is physical distance, vertical axis is time. The time interval between T sub I and T sub R, that's a phase of inflation. After T sub I, standard Big Bang cosmology. This length, which I show with my cursor, this is a Planck length. This scale is the Hubble radius, the Hubble horizon. And the way that I drew this sketch is that the trans-Planckian censorship conjecture is marginally satisfied. So the Planck length at the beginning of inflation grows to exactly the Hubble length at the end of inflation. So inflation cannot last longer than I drew here. On the other hand, if inflation is to be successful, then scales that we observe today have to start out inside the Hubble radius at the beginning of inflation. Otherwise, we lose our structure formation scenario. And again, I drew this condition to be marginally satisfied. So the TCC gives you an upper bound on the duration of inflation, demanding that inflation be successful at solving cosmological problems, gives us a lower bound on the duration of inflation. And the question is whether these bounds are consistent. And obviously this depends on where the Hubble horizon is located compared to the Planck length. The higher the energy scale of inflation, the closer the Hubble horizon is to the Planck length, and the more difficult it is to make these two bounds consistent. So, oops, I went the wrong direction. So the trans-Planckian censorship conjecture implies an upper bound on the duration of inflation, demanding that inflation is successful, gives rise to a lower bound on the duration of inflation. So T sub star, that's the beginning of inflation. This is the current Hubble radius, which needs to be smaller than the Hubble radius at the beginning of inflation. So if you combine these two equations, you find that there's an upper bound on the energy scale of inflation. And this is very, very small compared to the energy scale where inflation is usually assumed to happen. And if you have inflation, which is consistent with this bound, then you get an utterly, utterly negligible amplitude of primordial gravitational waves. Okay, good. So hopefully I've persuaded some of you that effective field theory analyses in a rapidly expanding universe have problems, and that these problems are particularly bad for inflation, because inflation uses an exponentially expanding background. Okay, so now I'll remind you that inflation is not the only successful early universe cosmology. And by successful, I mean an early universe scenario which is able to reproduce this beautiful data for the angular power spectrum of microwave anisotropies. So angular scale, power, the black dots are the data from WMAP, and this red curve is a 6-parameter fit. And this fit was first derived by Zeldovich and Zunyaev 10 years before inflation. And here's a plot taken from the Zeldovich-Zunyaev paper. And this plot shows time, vertical axis, co-moving coordinates, horizontal axis. This diagonal line is the Jeans length, which before recombination is identical to the Hubble horizon. And as Zeldovich and Zunyaev argued back in 1969, 1970, and in parallel Peebles and Yu, if you assume that there are primordial perturbations on super Hubble scales at early times with a roughly scaling line spectrum, and that was known to be a spectrum which gives good agreement with the distribution of galaxies. This was already known back in 1970. Then these fluctuations will be frozen on scales larger than the Hubble radius, and they will start to oscillate when they enter the Hubble radius And different wavelengths, therefore, undergo different number of e-foldings of oscillations between when they enter the Hubble radius and when we catch them at recombination, when the microwave background is released. And these different numbers of e-foldings gives you exactly these acoustic oscillations. So the physics of the acoustic oscillations was well known 10 years before inflation. So here is what I just said. Given a scale invariant power spectrum of adiabatic fluctuations on super Hubble scales before recombination, that is known to give the correct power spectrum of galaxies. That predicts acoustic oscillations in the CMB angular power spectrum, and it predicts the baryon acoustic oscillations in the matter power spectrum. So now, how does one get a successful early universe cosmology that gives us this first point? So first of all, we need the Hubble radius to be much, much smaller than the horizon in order for the early universe scenario to solve the horizon problem, the standard Big Bang cosmology. We need scales of cosmological interest to emerge inside the Hubble radius at early times if we want a causal mechanism for generating perturbations. And finally, we need the mechanism to produce a scale invariant spectrum of curvature perturbations. And in inflation, all these criteria are indeed satisfied. The horizon is exponentially larger than the Hubble radius. Scales of cosmological interest today emerge from inside of the Hubble radius, and the time translation invariance of this inflationary phase generates these scale invariants of cosmological perturbations. But inflation is not the only mechanism that satisfies the criteria. A bouncing cosmology can also satisfy the criteria. So here is what I'm assuming in this bouncing cosmology: time, scale factor. I'm assuming that the universe starts in a contracting phase. There's some new physics whose description we need to go beyond effective field theory. And there's a direct transition to the standard Big Bang phase of expansion. This is the corresponding space-time diagram, with this being the Hubble radius. And you see the horizon is infinite. So criterion one satisfied. Scales that we observe today start out inside the Hubble radius sufficiently early during the contracting phase. And if the fluctuations are generated as vacuum fluctuations in a matter-dominated phase, we get scale invariant curvature perturbations. The third scenario, the scenario that I'll be actually talking about, is an emergent scenario where we assume that there's an emergent phase, which I will describe as a quasi-static phase. So scale factor as a function of time, quasi-static, phase transition directly to the radiation phase of expansion. That gives rise to this space-time diagram. So quasi-static phase, horizon is infinite, Hubble radius is infinite, phase transition to standard Big Bang expansion. Hubble radius is this diagonal line. And you see horizon is infinite. Scales of cosmological interest today start out sub-Hubble in the emergent phase. And as I will show you, thermal fluctuations in this emergent phase generate a scale invariant spectrum of cosmological perturbations. So the bottom line from this part of the talk is that there's more than one early universe scenario which is consistent with current observations. Okay, so now I don't want to give you the false impression that inflation is ruled out. But based on the Transplanckian censorship conjecture, you do need your model of inflation to be based on non-perturbative physics. And there are indeed proposals, for example, by Giyad Vali. He and his collaborators have constructed an inflationary model based on inflation being a condensate of gravitons about Minkowski spacetime and non-perturbative construction. And colleagues of mine at McGill, in collaboration with others, have a construction of a finite duration inflationary phase as a coherent state in string theory. Now, in bouncing cosmologies, and again, if you want to construct a bouncing cosmology, I think you should consider an ekpyrotic bouncing cosmology, where the contracting phase is given by a very slow period of contraction. And I saw that Jean-Luc Lenos is connected here. Jean-Luc Lenos has done a lot of work on this. So if you want to construct a bouncing cosmology, you again need to go beyond an effective field theory description to get the bounce. So challenges for the ekpyrotic cosmology or for bouncing cosmology is how do we get the bounce? How do we get the scaling band spectrum of curvature perturbations? And what happens for gravitational waves? Now, I should also mention that in non-local theories of gravity, there are also ways to get bouncing cosmologies, very interesting ways. So, but we need to go beyond standard local effective field theory. Okay. I think in light of time, I will skip over this slide. I will just advertise that we have a proposal for a non-singular ekpyrotic bounce, where we add a string theory motivated S-brane to the effective action. So our effective action has a string motivated term, which resides at one particular point in time, and it has zero energy density, is negative pressure, and therefore it mediates the transition between contraction and expansion. Okay, but today I will be developing a emergent cosmology. And so I'll remind you of a toy model of obtaining an emergent cosmology, which is string gas cosmology. So this toy model is based on assuming that there's some space-time and assuming that matter is a gas of fundamental strings. And this gas of fundamental strings is very different from a gas of fundamental point particles. There are new degrees of freedom, oscillatory modes, which lead you to the fact that in thermal equilibrium, there's a maximal temperature. And there are winding modes, which lead to a new symmetry, the T-duality symmetry, which says that physics on a torus with large radius is equivalent to physics on the torus of small radius. So if space is a torus of radius r, there are momentum modes, winding modes. There's a duality symmetry. If we replace r by 1 over r in string units, we exchange momentum and winding mode quantum numbers. We have a duality. And hence, if we look at thermodynamics in on such a toroidal background, so r is the radius of the torus, capital T is the temperature. If we start with large radius torus, we contract the torus, the temperature rises, but the temperature never exceeds the Hagedorn temperature, the maximal temperature. In fact, if the torus shrinks sufficiently, the temperature goes back down. And you see that this picture motivates the assumption that here we have a quasi-static phase, and that we then make contact with the emergent cosmology paradigm, which I described a little bit earlier. However, we haven't given equations for the emergent phase. So I'm just postulating based on this thermodynamics that there will be this emergent phase in the dynamics. And this is now what I will try to describe today, a model for the emergent phase, which is based on physics, which goes way beyond an effective field theory description. But I have to remind you of one more thing, namely how we compute density perturbations and gravitational waves from thermal fluctuations. Because in this emergent phase, the fluctuations will be thermal and not vacuum, because our emergent phase will be a thermal state. So again, this is the background, which I'm assuming an emergent phase, and we have thermal fluctuations in this emergent phase. So we have a partition function, a finite temperature partition function, and with this finite temperature partition function, we can compute matter correlation functions. So therefore, what we do is we compute the matter correlation functions in this phase, and then mode by mode, when the mode exits the Hubble radius, we compute the induced density perturbations and induced gravitational waves based on the perturbed Einstein equations. So this is the method to compute density perturbations and gravitational waves from an emergent phase. And I'll let you stare at this slide because this is fairly important. So, and I will be using that in my matrix cosmology. Okay. So concretely, if I want to compute density perturbations and gravitational waves, so here I write down the metric in an expanding universe in conformal time using the density, the curvature perturbations in a particular gauge and the gravitational waves. Then the curvature perturbations are given by the energy density fluctuations, and the gravitational waves are given by the off-diagonal pressure perturbations. And these correlation functions are given by partial derivatives of the finite temperature partition function. Okay? So the density perturbations are given by the specific heat capacity. The specific heat capacity is given by the derivative of the internal energy with respect to temperature. And for a string gas, we get this holographic scaling of the specific heat capacity and plugging this back into the density perturbations and combining that by this equation gives us the curvature perturbations. And this gives us a scaling invariant spectrum of curvature perturbations from this emergent phase. So scaling invariant like for inflation, and a slight red tilt like for inflation. We can compute the gravitational waves. This gives us, with this string theory input, it gives us a scaling invariant spectrum of gravitational waves like for inflation, but it gives us a slight blue tilt for the spectrum, unlike inflation. And the blue tilt comes from the fact that this factor, which is contained in the finite temperature partition function of the string gas, occurs in the numerator for the gravitational waves and in the denominator for the curvature perturbations. Okay, so you see here I've given you a toy model for an emergent cosmology. I've shown you how you can get scaling invariant cosmological perturbations, scaling invariant gravitational waves. And I've shown you that we get predictions with which this emergent scenario can be differentiated from the predictions of inflation. However, we do not have equations for the emergent phase in string gas cosmology. So this is the Achilles heel. And now, in the last 6 minutes of the talk, I will try to construct the dynamics of the emergent phase from matrix theory. So the starting point is the BFSS matrix model, which is a proposal for a non-perturbative definition of superstring theory. So the BFSS matrix model is a quantum mechanical model of 9 n by n Hermitian matrices. So there's no space, there's no singularities. In fact, there is a 10th matrix. And I'll show you the Lagrangian in a minute. And so we will take this matrix model and we will take the n going to infinity limit, the 12th limit. So this is the Lagrangian. There are 9 matrices x sub I. They are fermionic partners. And this is a covariant derivative term, which contains a 10th matrix. There's an eta mu nu symbol, which is used to raise and lower the indices. And so this is our starting point. Okay, and this is the limit that we would be taking. N goes to infinity, keeping lambda fixed. and lambda is related to the string parameters, the string coupling constant, and the string length in this way. So this is a starting point. Now we will consider this matrix model in a high temperature state. And it is known that at high temperatures, the bosonic sector of this BFSS model is equivalent to the bosonic sector of the IKKT matrix model, which is a matrix model without space and without time. And it is given by this action and by this partition function. So here we have 10 matrices, A, capital A, superscript small a, and the fermionic partners. So this is the IKKT matrix model. Now, since these are Hermitian matrices, we can diagonalize one of these matrices. So we diagonalize the temporal matrix, and the eigenvalues become emergent time. And this is continuous in the n going to infinity limit. Now we will work in a basis in which A naught is diagonal, and the diagonal elements, we will list them in ascending order. And it is known that the A sub I matrices, they decay in this basis when we go away from the diagonal. So what we are going to do is we are going to take small n by small n blocks of these spatial matrices centered at the diagonal and located a distance t down the diagonal. And we will take varying values of n. Okay, so this is illustrated here. This is my emergent time. For each temporal variable, we will take this spatial matrix, and we will consider various sizes of this matrix. And that then gives us, for any small n, it will give us a spatial extent, which is the trace of these eigenvalues of these small n by small n blocks. So n we identify as co-moving distance, xi we identify as physical distance, and that then gives us the diagonal components of an emergent metric. So we get emergent time, emergent space, and an emergent metric. And all of it is continuous in the capital N going to infinity limit. And local Lorentz invariance emerges since we have the eta mu u symbol inbuilt in both actions. Okay, now it is known from numerical work that in this high temperature state, there is a phase transition, that only 3 of these spatial dimensions become large, 6 of the spatial dimensions remain small, string scale, which is a phase transition which we understand very well in string gas cosmology, but we don't really understand the physical origin of this phase transition in heuristic terms in a matrix model. We are still working on this, and I'm sure we'll be able to come up with a good heuristic explanation. Okay, so now we assume that this phase transition works also in the BFSS matrix model, and again, we are working on showing this. Okay, so you see we are almost finished now. We have this matrix model, we have a partition function. So now we can take partial derivatives of the finite temperature partition function with respect to time and with respect to the emergent space. We obtain energy density and pressure fluctuations, and therefore we can compute density, curvature perturbations, and gravitational waves. So finite temperature partition function of the BFSS matrix model, the internal energy, derivative of the internal energy with respect to time, with respect to temperature gives us the density perturbations, and we actually expand the matrices in a Matsubara expansion to evaluate these internal energies. And for details, I refer you to our paper. So we find that the zero mode gives us a Poisson contribution to the spectrum, but it is the next to leading terms in the high temperature expansion which dominate at infrared scales. And they give us a contribution to the internal energy, which depends on the emergent volume via this. And so we basically find the density perturbations and pressure perturbations. I brought back here. The pressure perturbations don't involve this term. They only involve this term. This term gives us a scaling invariant spectrum. This term gives us a Poisson spectrum. So bottom line is that in this emergent matrix model cosmology, we get a scaling invariant spectrum of curvature perturbations on infrared scales with a Poisson ultraviolet contribution, and we get an overall scaling invariant spectrum of gravitational waves. And the amplitude of the spectrum of curvature perturbations is given, like in string gas cosmology, by the ratio of the string scale to the Planck scale to the 4th power. So bottom line is that we obtain the same results as in string gas cosmology. So to conclude this part of the talk, the BFSS matrix model seems to yield emergent space, emergent time, and an emergent early universe phase. The horizon problem is automatically solved, but there are lots of open questions. We don't understand the phase transition between the emergent phase to the standard Big Bang phase, although I'm sure that it works exactly the same way that it works in string gas cosmology. Also, we don't yet know how the flatness problem is addressed. But again, I'm confident that we will soon come up with an answer. And in parallel, we'll also be able to answer this question. Okay, so to give you overall conclusions, and I didn't even get the 5-minute warning yet, but I should have gotten it. So hopefully I've persuaded you, hopefully I've persuaded all of you that in light of the transplanted censorship conjecture, we need to go beyond point particle effective field theory if we want to describe the very early universe. So now there are various ways to go beyond point particle effective field theory. And here in this talk, I've explored one way, namely to start with the BFSS matrix model, which is a proposal for non-predominant definition of superstring theory. And I've argued that if we take this matrix model, we consider this matrix model in a high temperature state, then we get emergent time, emergent space. The thermal fluctuations in this state give us a scaling invariant spectrum of cosmological perturbations and gravitational waves. The spectrum of cosmological perturbations have a Poisson ultraviolet tail. So thanks for paying attention.
I think we're over for this really nice talk. Are there any questions, either locally or on Zoom? Yes, there's a question by Ivano. Just 1 second. Please speak up.
Hi, thanks for the very nice talk. Can you hear me?
Yes.
All right. So I was wondering if you, I'll speak to you stand up. Okay. I was wondering if this kind of emergent cosmology from the BFSS model is related somehow to the analogous emergent cosmology proposed by Harold Steinhacker and collaborators in the IKKT matrix model.
Okay, I'm not sure that I understood. You asked me whether the BFSS matrix model is related to IKKT or related to which?
I'm just asking if these two. Oh, okay. So if these two works, so the emergent cosmology in the BFSS is related somehow to the emergent cosmology in the IKKT model that was proposed recently by another group.
Yes. So you see here, I stated it, so they are definitely related.
Yeah.
Now there are various groups that have been exploring the cosmology of the IKKT matrix model. I'm familiar with the work of Steinacker, who are looking at the representation of the algebra of the IKKT model in a background space-time.
Yeah.
So, I guess our model is, our approach is a bit more fundamental because we are really getting the emergent space and time.
Yeah, that's the impression I got. Thank you for the comment.
Okay, there's another question on Zoom by Jean-Luc Blenet.
Some sort of question.
Hi, Robert. Thank you for a nice talk.
Hi, Jean-Luc.
I was wondering if you say you start in a thermal state for the matrix model.
Yes.
I was wondering, what is the real justification for this? I mean, in cosmology, typically we think of the universe as being not in equilibrium. So what is the motivation for starting in a thermal state, which to me sounds like something that would be in equilibrium and would not lead to something evolving in time?
See, we have a matrix model, we have no space. And to me, there are only two distinguished states, either the vacuum state or the thermal state.
But do you have time already? If you
Yes, we have, in the BFSS model, there is a time. There's a temporal variable. And this is why we can make sense of temperature.
Right, okay. And is this Euclidean time to start with then, or?
Yeah, so we consider the Euclidean, we consider the finite temperature partition function.
I see, okay. And then from this, you then see the emergence of space and the expansion of the universe.
Yes. So let me go back down here. So see, this is a starting point for our computations of the observables.
Mm-hmm.
The BFSS finite temperature partition function.
And in a sense, is the emergence of space then sort of a necessary consequence?
Yes, I think it's a necessary consequence because we want to. So this was our goal. We want to get emergent space.
Mm-hmm. Yes. Okay, thanks.
Okay, I think there's another question here locally by Alessia.
Yeah, so can you hear me?
Yes, but maybe you can go closer to the microphone because there's an echo if you're too far back.
Okay, can you hear me now?
Yes, now I can hear you well.
Okay, good. So I have like a couple of questions. So one is about your conclusion. So you state that essentially with this model you can recover the same results as in string gas cosmology. So a first question that I would have is like, what is the advantage of using this model over string gas cosmology?
Yeah, so the Achilles heel of string gas cosmology is we don't have equations for the emergent phase.
Okay, I see.
I view this as a completion. And maybe I should also advertise that Wafa and collaborators have another proposal. And according to their proposal, the emergent phase is a topological phase. And then you have a phase transition to the radiation phase.
Mm-hmm. Okay, I see. I will look for this. And the second question that I had is I didn't really get whether within this model the TCC is automatically realized, and if not, if the TCC can put constraints on the rush between the string length and the Planck length, for instance, like any constraint.
That's right. Yeah, that's a very good question. And so bouncing cosmologies and immersion cosmologies are consistent with the TCC as long as the energy scale at the bounce or in the immersion phase is smaller than the Planck scale. And so for the string scale, it means that the string scale should be lower than the Planck scale.
Mm-hmm. Interesting. Okay. Thanks.
Okay, thank you. I think we have to move on now. Let's thank Robert again.
So I stop sharing.
Yes, please. Thank you. And we are going on with Ivano Basile here locally. Just give us 1 second to set everything up. Okay, Ivano, please go ahead.
All right, let me just test out. Okay, I can scroll. Okay, so hi everyone. And first of all, I would really like to thank the organizers for this invitation, and especially Luca for not only inviting me very kindly, but also insisting. And that I came in person, and this was definitely the right choice. So very great conference and organization. All right, so this talk is about the paper whose archive number you can read at the bottom of the slide. And it's a paper that I wrote together with Alessia. And it, as you can see from the color coding, it's about two main ideas. One is asymptotically safe gravity, and the other is the swampland problem. So I will first start slowly introducing both concepts, and then I will tell you about the connections that we started to investigate in this work. And so the presentation should be fairly short. So I think there will be time for questions and interruptions while I present these ideas. So feel free to interrupt me at any moment or make any comments. All right. So first of all, let me explain very briefly what the swampland is. So this very nice figure that I essentially stole from the very popular review by Rampalti. So credits to Aaron for the picture. This figure represents how the space, the set of gravitational effective field theories changes along the energy scale. Think of, picture the renormalization group flow, the possible RG trajectories undertaken by the gravitational effective field theories. And the idea is the following. At low energies, in principle, we are able to write down an incredibly vast set of effective field theories by virtue of the fact that we can just put basically any value for any Wilson coefficients for any higher derivative corrections. We can add any kind of matter that we like, as long as gauge anomalies cancel and all that. So a priori, just from the point of view of effective field theory itself, at very low energies, there doesn't seem to be any strong reason to exclude any of these effective field theories. However, once we switch to think about the UV, the high energy physics, the requirements for UV completion, for the existence of a UV completion with gravity, are much stronger than that. And the idea is that at high energies we have, let's say conservatively, a very small number of possible UV completions, ideally one. Even if we don't assume anything about what this UV completion could be, the idea is that the possible low energy effective field theories that stem from this UV completion via RG flow is a very small subset of the possible, of all of the set of all possible effective field theories that we can write down naively, right? And this set of effective field theories that can be UV completed in the presence of dynamical gravity is called landscape in this context. And the remaining, all the effective field theories that are actually inconsistent as a quantum theory of gravity is called the swampland. They are the theories that we don't like, we want to exclude, right? And so this is what the swampland is, but the swampland program as a research program is essentially the idea of, instead of looking for the theories in the landscape, so searching for consistent theories, the idea is to do the opposite, to search for what can be excluded, right? So, logically speaking, if we had perfect information and perfect computational capabilities, these two approaches would be exactly equivalent. It turns out that in practice, with our limited knowledge, often the two approaches are quite different in their feasibility and their results. And so it is indeed worthwhile to investigate quantum gravity in this roundabout way of excluding inconsistent theories and shaving off the set of effective field theories down to what looks like a consistent landscape. And so in order to do this, the research community in this field has formulated, proposed, and studied a number of criteria. So these can be named swampland conjectures, swampland criteria, as one prefers. And this is a list of criteria that an effective field theory must satisfy in order to admit a UV completion with gravity. And not only these criteria form just a list, they are actually interconnected. They form a network of ideas and conjectures, and they imply each other in very deep ways, and they are really pushing us into an interesting new direction in the past, I would say, 15 years or so. All right, so this is what the swampland program is. And in particular, in this talk, because the proposal, the main motivation that drives us is conceptual in nature, the idea is to apply the swampland program to a particular approach to quantum gravity, which is asymptotic safety. And so we must, start easy. So instead of taking the whole list of known proposed swampland criteria, we start slowly and we pick two, essentially, the two that we decided that were easy enough to test in an easy enough toy model to start looking at these kinds of ideas. The first one is the weak gravity conjecture, which is perhaps the most famous, most discussed of these swampland conjectures. And it stipulates that in a consistent theory of quantum gravity with U1 gauge invariance, there should be a state which is charged and whose mass is lower than its charge in Planck units. Right, so this is expressed by this inequality, and this order one constant, although I left it general here, usually can be computed precisely within a specific model, and it's related to the extremality bound of macroscopic black holes, actually. Now, the requirement for an effective field theory to admit such a state a priori doesn't come from any consistency, anomaly cancellation, or anything like that, but it is suggested by low energy arguments. So usually in this swampland context, these criteria are both motivated by actual UV complete frameworks, and 99% of the cases this is done within string theory because this is where this program was born originally. But there is a complementary approach, which is low energy reasoning, usually based on black hole physics, classical black hole physics, and also on considerations in cosmology and inflation, such as the comments that Robert made about the Transplanckian censorship conjecture. This is essentially based on reasoning about inflation, etc. So in the case of the Whig-Rayleigh conjecture, one of the low energy motivations, the semi-classical motivations for it, is that black holes that are not protected by any particular symmetry, such as supersymmetry, should be able to decay, right, without exposing naked singularities. So this requirement, which is usually expressed in terms of the opposite inequality for macroscopic black holes, implies essentially that if a black hole that is very close to extremality decays, it should remain above the extremality bound, such a way that no naked singularity appears, and it has to be able to decay. Otherwise, we should have some symmetry that protects it, and this requires the existence of such a state. Of course, there are many other motivations for the Whig-Rayleigh conjecture. This is one of the most solid conjectures that have been proposed. So this is one of the two main ideas that we will test within a toy model of asymptotic safety. And the second, well, let me first explain more about how we will test it. So this is the raw idea of the Whig-Rayleigh conjecture. But what happens is that the extremality bound itself changes along the RG flow due to the inclusion of higher curvature corrections, or in general, higher derivative corrections in the field. Now, what we will do is we will investigate essentially the simplest model where the requirements of asymptotic safety can be formulated, which is quadratic gravity. And in quadratic gravity, there are, as the name suggests, quadratic corrections in the curvatures, weighted by some Wilson coefficients, right? And these Wilson coefficients do modify the extremality bound in this form, at least for macroscopic black holes. And the idea is that the Whig-Rayleigh conjecture implies that this particular combination that I defined, delta, be positive. And this combination, turns out, depends on the charge to mass ratio, the naive extremality parameter of black holes. And you see, this combination involves the Wilson coefficients. So it is a constraint that shaves off part of the naive set of effective field theories, which in this case would be the space spanned by these Wilson coefficients. So we will investigate in detail how this happens, and we will compare with the values of these Wilson coefficients that are allowed by the condition of asymptotic safety, namely that these coefficients arise from the RG flow stemming from some UB fixed point. So this is the story about the Whig-Rayleigh conjecture. And then we're also going to test something else, which is the de Sitter conjecture. Now, the de Sitter conjecture is definitely less grounded than the Whig-Rayleigh conjecture in the context of rigorous enough motivations and derivations of it. But it is motivated by various considerations related in particular to cosmology. And indeed, there is a relation between the de Sitter conjecture and the TCC that Robert explained in the previous talk. And essentially the de Sitter conjecture is a precise mechanism that obstructs de Sitter vacuum. So it is essentially motivated by the fact that, at least in string theory, it's very hard, if not maybe impossible, to construct classical de Sitter vacuum. And it originates from the fact that whenever there is a scalar potential for some scalar fields in an effective field theory, it turns out that when looking for critical points with a positive cosmological constant, there is an obstruction to this. And the obstruction is that I guess this inequality signs should be reversed. The modulus of the gradient of the potential in the space of scalar fields, it's always larger than some order 1 constant times the potential itself, which means that there is no critical point with positive value of the potential. And the idea is that this obstruction, this coefficient C, is order 1 in Planck units. So this is really, in some sense, Planck scale effect. There is a Planckian obstruction to the existence of the system. Now, this construction, this formulation was refined in many works. It was extended by an additional requirement about the Hessian matrix of this potential in the space of scalar fields. And so in this particular work, we're going to focus only on the first constraint because it turns out that it's the only one that's necessary. This extra constraint doesn't play any relevant role, but it can be in principle investigated. And not only that, but I was hinting before at the connection between the de Sitter conjecture and the TCC. And it turns out that the connection is that for in asymptotic regimes of the space of scalar fields, which in our context will translate into small curvatures in the effective field theory, this value of C, this particular value of C, is the one associated to the TCC. Not only that, but it was shown that this particular value also arises from other considerations, such as the idea that this bound be consistent under compactifications of extra dimensions. So all in all, this is the bound that we're going to investigate. And an even more precise statement is that this bound be realized for sub-Planckian field ranges. Right? So for like thinking about inflation, the idea is that the distance in the space of scalar fields traveled by the scalar along the expansion be sub-Planckian in the sense that be bounded by an order 1 constant in Planck units. This is the de Sitter conjecture. And again, one thing that one can do in this framework is take a set of effective field theories with a scalar potential and just compute the ratio between the modulus of the gradient and the potential itself in regions where the potential is positive, and see if these bounds satisfied. And these bounds constrain the possible values of the Wilson coefficients. So you see that this procedure in principle is very concrete. Right? We have a set of effective field theories with some parameters, and we constrain these parameters using this criteria. So this procedure, you see, it lives at low energies. It doesn't require any extra information. And this procedure gives us a subset of the starting space of effective field theories. So in order to compare this with a specific approach to quantum gravity, the idea is to take this subset of effective field theories that are apparently consistent with Swampland criteria. They're not excluded by the Swampland criteria. And we compare this subset of effective field theories with the subset of effective field theories that arise from any one given approach to quantum gravity, let's say. And this, this is the landscape pertaining to any specific approach to quantum gravity. Now, this has been done extensively in string theory, again, because this program was born in the field. And so, in the last 10-ish years, this program was really pushed to some very technical heights, and very large classes of effective field theories, mostly supersymmetric, were tested against this criteria, and essentially all the known examples work. However, what has not been done so far was to test these ideas in a different context, right? And the most natural thing, the simplest thing that we can do is to take, let's say, a toy model of asymptotically safe gravity, which will give us a certain subset of effective field theories. and test that against the subset of effective field theories not ruled out by Swampel conjectures. That's a very simple idea, and this is what I'm going to present. Now, what is asymptotic basic gravity? This is the second keyword of the talk. Now, this should be probably more familiar, and the idea is that the perturbative non-renormalizability of gravity is just an artifact of perturbation theory, and really non-perturbatively there should exist. The proposal is that a UV fixed point of non-perturbatively exists, and of course not only that, but the UV critical surface should be parameterized by a finite number of parameters in such a way that the low energy physics is parameterized by a finite number of parameters. So how does one go about to investigate this idea in practice? Because of course, it's easy to say non-perturbative quantum gravity, yay, but in practice it's very hard to investigate. And here I'm just going to present two approaches. Right? And one approach is in spirit similar to lattice field theory, and it's the approach of dynamical triangulations, where one just constructs a discretized path integral in a certain way that doesn't rely on perturbation theory around any given background, and seeks a continuum limit, right, at a critical point in order to recover a continuum limit. And this ought to define non-perturbative theory, but the practical obstacles of this formalism is that it's computationally hard to work with macroscopic, macroscopic number of lattice elements, let's say. So it's hard to build, macroscopic universes in this way, as far as I understand. On the other hand, there is a continuum approach, which is probably more widely studied in this context, which is the functional renormalization group, which is essentially a way to trade. Instead of working with perturbative renormalization group, one works with a different approximation of an RG flow equation for the effective action that ought to be exact, or at least perturbatively exact. Instead of expanding the full RG flow within the full space of effective actions perturbatively, one expands it in a different way using truncations. Now, there are people here that are way more expert than I am in this context, but the idea is very clear, and it's systematically improvable. And one takes essentially a finite dimensional subspace of the space of action functionals, consistent with any given symmetry, field content, and all that. And one projects the flow equation here. I just wrote a specific flow equation, which is the vectorish one, which is most useful in practical cases. So one projects this equation along a finite dimensional subspace, and then the resulting flow can be often investigated without relying on any perturbative expansion. Of course, this comes with a price, and the price is that the conclusions are not necessarily, controlled with an error margin that is known, but whatever conclusions there are systematically, they can be systematically improved upon by enlarging the truncation space. Now, we won't do any of this. Again, since the starting idea is very conceptual in nature, it's testing Swampel conjectures within asymptotic safety, the simplest starting point is to just do a very simple perturbative one-loop renormalization group flow in quadratic gravity. That's the toy model we're going to work with. So this is the game plan, right? We take a toy model of asymptotic basic gravity, which turns out to be the simplest one is one-loop quadratic gravity. We look at the RG flow of one-loop quadratic gravity, which actually does contain a UV fixed point. Of course, it's not reliable in any quantitative sense because the fixed point itself cannot be perturbative. So, take the final conclusions with a grain of salt. This is a proof of concept of what can be done. Right? So starting from this toy model, one can extract the space of effective field theories allowed by the requirement of asymptotic safety. One starts from the fixed point, one explores all the relevant directions stemming from this fixed point on the UV critical surface, and all these RG trajectories end in the IR in some effective field theory, set of effective field theories with some set of Wilson coefficients. And this will not, in general, cover all of the space of effective theories. And then we take the same model and we study the constraints imposed by the weak gravity conjecture and the de-Sitter conjecture, and we identify corresponding space of effective field theories consistent with those requirements, and then we compare the two. That's the very simple idea. So again, the toy model in concrete is this one, and you see that there are, up to a convenient rewriting of the Lagrangian, there are essentially three dimensionless couplings. So the coupling of the Ricci squared, the Ricci scalar squared, the coupling of the Weil tensor squared, and then the dimensionless combination of cosmological constant and Newton constant. And then there is the coupling of the topological, at least in 4 dimensions, topological Gauss-Bonnet term, which turns out not to play a very important role in this discussion. So we will look at the space of effective field theories spanned by these 3 dimensionless parameters. Simple as that. And again, we look at this theory at one loop to see what the space of Wilson coefficients, these 3 Wilson coefficients consistent with a UV fixed point is. So I will spare you the technical details, but these are the one-loop beta functions with some definitions of these dimensionless couplings. And from these beta functions, one can extract the RG flow, in part analytically, in part numerically. So the fixed points can be written down in a reasonably explicit way, and the RG flow of the classically marginal parameters can be also written down explicitly. What cannot be written down in closed form is the RG flow for G and lambda, the classically relevant parameters, but this can be done numerically. So we start from these analytic expressions of the RG flow of the classically marginal parameters, starting from certain deformations of the UV fixed point. And then, so these are the results. These are the flow diagrams of the classically marginal deformations, starting from a UV fixed point. And so you see these in these axes, there are, instead of the couplings, the deformation, the deviation of the coupling from the fixed point value, and plugging in this flow, which is expressed in closed form here, inside the flow equations. I mean, the first 2 beta functions for the classically relevant couplings, one can numerically determine the flow of these couplings as well. Now, the idea is to see where these flows end, or at least how these flow, what the asymptotic infrared behavior of these flows is. And in order to do that, you see the RG time parameter is usually expressed as a function of an arbitrary scale, which is the scale where the classical action lives, K0. And in order to get rid of this arbitrary scale, we can evaluate the RG running, at a different value of this parameter T, which is this particular combination that involves the dimensionless Newton coupling, which is related to the Planck scale, right? And this is because we like our low energy effective field theories to be expressed in terms of the Planck scale instead of an arbitrary scale. And by this substitution, one is left with no arbitrary scales, and instead the RG time is re-expressed as a function of the Planck scale and the actual RG scale K. And so the idea is to investigate how the flow of the Wilson coefficients of these couplings behaves asymptotically as k goes to 0 or t goes to plus infinity. Right? And it turns out that not all couplings are swept by this flow. So this is the key point. The couplings, the values of the Wilson coefficients that are reached by flows that start from the UV fixed point are not, the full space of couplings, but rather this particular plane that can be determined by a numerical fit or some analytic considerations. So you see, the first part of the program, at least in the toy model, is successful. We did determine the subspace of effective field theories in this very restricted setup, which stem from a UV fixed point. Again, in a very unreliable toy model. So now the next step, the second step of the plan, is to determine the subspace, which a priori is an independent thing, that is consistent with the swampland bounds. Now, plugging in the various values of the coefficients in our parameterization for the positivity bound imposed by the weak gravity conjecture in particular, we have a bound that essentially doesn't constrain much at all compared to what the asymptotic safety requirement does. In particular, it just requires that this lambda parameter be positive, but this is already required by the existence of the UV fixed point. And so really the only constraint that this requires is that the deformation from the fixed point value of the Gauss-Bonnet coupling be positive, but this doesn't really change much. It changes nothing in this picture. So there are no additional constraints coming from the weak gravity conjecture. The non-trivial constraints come from the de Sitter conjecture, and we investigated it essentially by replacing the f of r part of the effective action by rewriting it in terms of the scalar, let's say an inflaton-like scalar. And doing this with this particular quadratic f of r gives us fairly standard Starobinsky-like potential for the scalar field. And what we did was to just express the de Sitter conjecture bounds applied to this particular potential. Doing this, which requires a bit of numerics, gives us these regions that are allowed. And you see the various colors, various ranges refer to different values for the order 1 constants that are a priori undetermined by the de Sitter conjecture. The only requirement is that they be of order 1 in Planck units. So this is a range of possible regions allowed by the de Sitter conjecture. Now, putting everything together, we have our space of effective field theories allowed by these two particular swampland conjecture in this particular toy model, and this plane allowed by the requirement of asymptotic safety. Now you see that they mostly overlap in this region here, and it's a bit hard to see, but the paper contains this figure in various other orientations. And so the key conclusion here is that in this very limited toy model setup, the intersection is non-empty, but it's also not all of it. Right? The two spaces are not subset of each other, but they are not disjoint either. So this is the most generic possibility for two given subsets of this whole space of Wilson coefficients. But what does it teach us in the end? Well, any conclusion that we could draw from this calculation is, of course, completely unreliable, because for one, we investigated a perturbative RG flow outside of the perturbative regime, and for two, we only included the constraints of two swampland conjectures and not all of them. And of course, we don't know all of them. If we did, the problem of quantum gravity would have been solved already. So recalling these two facts, we can draw some conclusions with a grain of salt. And the conclusions are the following, namely, there are a few possibilities. So you see, if there are effective field theories allowed by asymptotic safety that are not, that violate swampland constraints, it could just mean that swampland constraints are wrong. On the other hand, if there are effective field theories allowed by the swampland conjectures that are not reached by asymptotic safety, it could mean that there exist other UB completions, right? Because the idea is that anything that's allowed by swampland constraints should be able to be UB completed to some theory of quantum gravity. So you see, there are various scenarios here, and so the point of this work was not to draw some precise conclusions, but rather to give a proof of concept of the fact that this, investigating swampland constraints in frameworks of quantum gravity different from string theory is perfectly possible. And in particular, again, despite the particular conclusions of this particular toy model that we investigated are, somehow unreliable, the extensions of this kind of study are very, very clear. It's, we can just add in more constraints coming from other swampland conjectures that I didn't list. And we can extend the reliability of the asymptotic safety framework that we use. We can use actual functional renormalization group calculations. We can extend truncations systematically. One can, invoke other methods like dynamical triangulations or any other method. So all in all, the extensions in various directions are very clear. And this is the key point I wanted to deliver. The conceptual idea is very simple. We just, gave a very first baby step into actually putting it in practice. But the extensions are very clear, and the research line ahead is just very wide open, essentially. So thank you for the attention.
Yeah, thank you, Ivano. This really nice. So, are there questions, either locally or on Zoom?
Sorry, go ahead. So I see something in the chat. Can I open the chat?
Yes, let's go first with the chat maybe, and then.
Oh, okay. Well, it's a message, but not a question.
Okay.
Thank you, Mikael. Very nice message.
Yes, from Leslie.
Okay, go ahead.
Thank you for a nice talk. Yes, I wanted to ask to understand. So basically, in this effective field theory, like when you check the conditions for the black holes with this extremality conditions or for the de Sitter, you use the. You take this effective field theory and you study classical solutions. Yeah, you don't really have like some quantum corrections appearing there.
No.
So as you said, just please reconfirm that in the IR you have this theory, and then it's basically deep IR, low energy action that you study classical solution of, and then on this you put some constraints, and for the swampland you want to check whether they are.
Yeah. So the constraints come from quantum gravitational considerations because of the decay of these black holes.
Yeah.
But the actual bounds, arise from classical solutions. But this is just one way to look at the weak gravity conjecture. Of course, it's somehow a roundabout way. We're looking at the spectrum of particles with masses lower than the charge by looking at black holes with masses higher than.
Okay, it's the inverse.
It's a way of studying this bounding effective field theory without actually looking at the charged states of the theory apart from black holes. So we're not including matter, but somehow we are still.
Yeah, there is a charge U1 field, so there is something of the matter origin.
Exactly. Now there are some technicalities about this U1 gauge field that I skimmed over because of lack of time, but you may have noticed that in our theory, there are no higher derivative corrections for the maxwell field. I just didn't put them.
Yeah.
And the reason is that even at one loop, it's just a technical limitation. Even at one loop, the RG flow of Einstein-Maxwell with higher derivative correction is insanely complicated. But there is a way out, and the way out is to assume that electromagnetic invariance that holds at the quadratic level holds also for higher derivatives. If one assumes that, there are no, all the higher derivative corrections can be expressed purely in terms of the gravitational curvature rather than the gauge field strength, which saves us the trouble of including those corrections. But if one wants to do away with this assumption, and I'm sure that some point do that, one would need to include the higher derivative corrections for the U1 gauge field as well, which is extremely complicated.
Yeah, but I think that at least at one loop you don't generate like f box f or something like that. I mean, at one loop, I guess you only generate f squared terms if they were not the first place.
Yeah. So the quartic the quartic terms in the gauge field do not normalize at one loop because of electromagnetic invariance. Yeah, this is true. But if one wants to do something like non-perturbative calculation within a certain truncation of the FRG, then the story may be different.
Okay. Yeah. So I wanted to ask you. So if you stick to this low energy couplings, I mean, you have some like this. They were of the higher derivative terms like C1, C2, C3. So how you said that? Okay, as a part of introduction, you said that you can, in principle, via functional G relate them to the fixed point values. But is there any other way, like for example, how you can relate this IR with the UV?
Well, within the framework of asymptotic safety, I don't know of any other way. Within in other frameworks, there may be a lot of other possibilities. Like in string theory compactifications, there are many other ways of constraining the possible values.
But you agree that the values that you have in IR, in principle, they are not identical to the ones that you
Absolutely
have in the UV. So in UV, you have some completed theory, UV complete with some values of this coupling, let's say of this C1, C2, C3, but then in IR, they are completely, I mean, a priori completely different.
They would be, expected to be completely different, but not only that, even from a single fixed point, which is the case in our case, there are infinitely many possible values of the IR couplings. And this is expected from the RG flow. The point is that the infinitely many values of the IR parameters are not all of the possible values. They, in this particular case, they span a hyperplane, right? And in general, they will span a subspace of dimension given by the dimension of the UV critical surface. That's just actually, the space is in some sense the UV critical surface.
So let me mention. Okay, there was some work of Roberto Procacci and also of Nobuyoshi Ota. I was also co-author when we kind of integrate the effective action exactly from UV to IR using the method of heat kernels. So basically, this is also one of the way how you can relate these things. I mean, to have the really scale-dependent effective action, and then we really see how the couplings, how they interpolate with the energy scale.
Exactly.
Okay, I think there is another question.
Luca?
What is
Okay, no, it was actually you partially answered, but it was just general consideration. Can you do you have the intention to extend this consideration to other quantum gravity approaches? I mean, it could be very useful to see the swarm plan of the various effective field theories, also from loop quantum gravity, and is it possible in principle or?
Well, in principle, yes, but the thing is, in order to do this comparison, one needs to be able to study, to look at the space of effective field theories that are compatible with any given UV completion. So you have to have the possibility of taking your whatever framework of quantum gravity is and giving a concrete low energy effective field theory, which is written in the usual language of field theory. And this is not the case for all the present approaches to quantum gravity, as far as I know.
Yeah,
So
that
you
was
have to
my
have-
impression. For Luke, maybe it's more complicated.
Exactly.
I think it's the problem that I mean they have the problem in writing effective theory.
Exactly. That's the point. So you need to have this fundamental. You have to have the possibility of linking the UB with the IR somewhat concretely at the very least.
I see.
Sure. Are there any last questions? We check also this.
Yeah, but he already asked.
Yeah. Okay.
No more raised hands.
Great. If this is not the case, let's thank Ivano again. We are perfectly on time for our next speaker. Anupam, are you there?
Yeah, I'm present.
Then please go ahead, share your slides. Okay, perfect. Anupam Mazumdar is our next speaker. Please go ahead.
Okay, let me. Yeah. So first of all, let me thank the organizers for organizing this wonderful workshop. And maybe I'm going to tell you something slightly different than what from previous talks. Is slightly geared towards experiment. And the title of my talk is Witnessing Quantum Gravity via Entanglement of Masses. In short, it's called QGEM. It's a protocol, QGEM protocol. And I'm going to tell you a little bit about the progress we have made so far in the past 4 or 5 years, what we have learned about how to do an experiment and what are the challenges we have. So it's a long-term goal, but nevertheless, I think it's a very interesting avenue from my perspective. And the reason is because our community, quantum gravity community, does need an experiment. So today what I will do is I will talk about the first paper of 1707, then I'll talk a little bit about these 2 papers. And on the same date, there was another group of colleagues, Mallet and Vedral, had a paper on the same day. And I would definitely request all of you to look into these 2 papers and weigh upon them. Okay, so as I said, that I think we don't need any introduction for this community. It's primarily meant for quantum gravity workshop for colleagues. And we would all agree, perhaps, that our community needs experiment very similar to what particle phenomenologists have done or any other fields of interest have done. And as you have heard from many speakers, that there are a number of approaches towards quantum gravity. But everyone would perhaps agree on here that in the low energies, the perturbative quantum gravity is a very successful way of describing the nature of perturbative quantum gravity. So I'll be talking about some aspects of perturbative quantum gravity, but we have to keep our minds open. Maybe we need to, there are certain ways, maybe we can also test certain different aspects of non-perturbative aspects of quantum gravity as well. So again, the effort is to test quantum nature of gravity. You can do it various different ways. And I have been putting quite a lot of effort in this direction through either in the black hole or a lab-based experiment. And today, as I said, that my focus will be mostly on this particular paper, which we wrote in 2017, a spin entanglement witness for quantum nature of gravity. And I'll tell you a little bit about what I have learned so far from my colleagues in this topic. Okay, so plan of my talk. So what I will do is that I will briefly introduce you the QGEM protocol. I will give you how to read the witness, because that's very important. And I will also highlight numerous challenges and what is the future program. And towards the end, if time permits me, I'll tell you even how to motivate quantum theory of gravity from experiment, because that's something which is interesting, Ivano, also. I mean, we always have been trying to build theories of quantum gravity from very much from the top bottom, but maybe it's something we can learn from also bottom up approach. So the two key things which goes into is the quantum superposition of geometry. So something which you have to mimic it in a laboratory. Of course, it's going to be very, very tiny effect, but nevertheless, given the advancement in technologies which we are seeing, maybe it is possible to even, capture these very tiny effects of geometry. Okay. So what are the key ingredients? So let me just jump into the topic. Of course, having said this, it has a huge history. It all started way back in the 1960s, mid 60s, when Feynman was talking about how to even, essentially superposition of masses and all these things. Some of these ideas essentially come from actually no other than Feynman himself. So some of the things which we are talking has some very much deeply taken from essentially Feynman's view. So one of the three things, so there are three key ingredients which we would need in order to test the really bona fide quantum nature of gravity, is that you need to have a quantum superposition of two massive systems. And I will tell you a little bit about the nanocrystals or other approaches, but you need some masses. And quantum superposition is something which you cannot mimic in a classical world. You want to establish an entanglement between these two systems. So they have two systems, like system A and system B. System A is in your quantum superposition, system B is in a quantum superposition. And you want to see the entanglement created between these two systems, between A and B. Again, entanglement is essentially a quantum correlation, which has no classical analog of entanglement. And the third ingredient, which is very crucial in understanding some of these aspects, which essentially come from, it's amazing that how physics are, topics in different areas of physics, they are interrelated. So it actually came from a quantum information side. It's known as classical communication cannot lead to entanglement, and I'll elaborate on that. But it has a very interesting, analog in even in field theory. And this is the part which essentially, when I realized, I started talking to the quantum information people. And one of my close colleagues, Bose, is really one of an expert in quantum information and quantum technologies. And he really helped me to understand, go deep into this area for doing an experiment. So just to elaborate a little bit on, there is no entanglement via classical channel. The idea is very simple. Suppose you have got an Alice on one end of Earth, and you have got Bob. Let's imagine that Alice is a quantum system, has a quantum system. Bob also has a quantum system. Both are doing quantum experiments. So whenever I'm saying quantum experiment, I mean maybe they're playing with superpositions or whatever, anything to do with quantum electron spin, for instance, whatever quantum matter as far as matter is concerned. And they're both doing some local observations, because you need to make local observations at the two ends to find out, maybe like tossing the coin. If the coin itself is a quantum coin, how many times you're getting heads up, how many times you're getting tails. So both of them are doing quantum experiments and making some certain operations, quantum operations, to measure what they are getting out of their experiment. But the key part of this theorem is that as long as they are interacting or classically communicating their results from A to B and B to A, the A and B are not going to get entangled. So it's impossible to generate or increase entanglement between A and B by local operations and classical communication. And sometimes in short, it's known as LOCC. And it was a theorem which was based on none other than father figure of quantum computing, is Bennett, Charles Bennett, and his colleagues, Wouters and other colleagues are also involved in this way back, and they discussed this way back in 1996. So what, in essence, what LOCC does is that it keeps the separable state, remains separable, and it cannot generate any further entanglement. Now, we are essentially coming from, we are all coming from some field theory background. So in the QFT, it's actually very easy to understand this consequence of this LOCC. So imagine you have got Alice and Bob at two ends, and essentially they are interacting. This interaction could be via anything now. It could be via photon, via graviton, or via gluons, anything you can imagine, any gauge bosons, any interaction between Alice and Bob essentially would lead to an entanglement. And in the context of gravity, I think we know people in our community have computed this kind of, essentially this is nothing but the two-body problem. And people have computed the Hamiltonian to I think 5.5 post-Newtonian order. So these are the well-known computations with arbitrary momenta, with arbitrary distances and things like that. So some of these things are very well established, but we won't need the precision to go for 5.5. We are happy with the lowest order, essentially 4pn, 2pn order, essentially, computations. So another aspect of quantum information, which is very helpful and which goes into this kind of establishing this experiment, is entanglement. As I mentioned, an entanglement, it has no classical analog. A simple way to understand this, that you have got subsystem A and B. And if the subsystem A and B are entangled, you can actually read that entanglement via witness. And it was used many, many times in past. Perhaps take an example of Bell's inequality, and Bell gave a witness for that. And the sigma x, sigma y, sigma z are nothing but the Pauli matrices. And in the Bell's basis, because it's this witness W is a basis dependent. So it depends on what basis you choose. And I give you two examples of that. So the Bell's witness is written as I have shown here. And in the Bell's witness, if the W is bigger than 1, then you can establish that the states of A and B are entangled. And as I said, since it's a basis dependent, you can construct different bases as well. Just to give you an example, suppose you take the basis which is given in equation 2. So there, your system is entangled if the trace of W rho is less than 0. So besides the witness, you can also come up with other ways to discuss entanglement, especially when your system is bipatrial system. So since we are going to deal with mostly bipatrial system, so there's another case, another witness you can, sometimes is known as concurrence, which is given in this formula. And in this context, if the C is a kind of like witness, if it is between 0 and √2, you will find that the states of A and B are entangled. So these are some simple mathematical way, or these are the essentially witness becomes my ruler and clock, because I want to make some measurement, and this is the way I'm going to read my witness. So, so I'm going to tell you some of these ideas, and some of these things have been already been present in archive. So maybe what I will do today is I will give a very simple example to convince you about this LOCC part and its counterpart, which is sometimes known as LOQC. LOQC stands here for local operation, exactly the same way as what we have discussed here, local operation. But instead of classical communication, we have a quantum communication or a quantum mediator, because we are after all dealing with quantum systems. So, so let me highlight this in a very simple toy model, even at the level of quantum mechanics, perturbative quantum mechanics, nothing beyond that. So suppose you imagine you have got two harmonic oscillators. You have red harmonic oscillator and blue harmonic oscillator. And let's say that I have switched on some interaction, which I denote by HAB. So initially, my states of A and B are given by, let's assume that they are vacuum states. But once I switched on my perturbation, the initial state psi I now evolves to final state psi f. And this we know how to compute it in perturbative quantum mechanics. We can do first order perturbation, second order perturbation to my eigenfunction and then eigenvalues, and I can find all the information from here. So this is what I have done. So if you look into the psi f, you see that very interestingly, this because once I switched on the interaction, what happens is the final state gets entangled if the last term is non-vanishing. And the last term is nothing but your correction to your energy eigenvalue. And so this is the, so here I have taken into a state to be some kind of number state, or you can call it a Schmidt basis. And so essentially what's happening is that when you switch on the Hamiltonian interaction, you are essentially populating your harmonic oscillator states to N or capital N, and you can compute the coefficient of C and M. So this is the very simple setup, which we all are aware of. So now let's apply this setup to perturbative quantum gravity. So this is more like a pedagogical, it's nothing very fancy, nothing complicated quantum gravity, just perturbative quantum gravity. And for the timing, assume that there's no other interaction. And we'll talk about the interaction later, because these essentially I cannot ignore the background interaction. I have to take into account, but just for the purpose of illustration for this part of the talk, let's assume there's only gravity and the mass. And let's imagine that these are simple harmonic oscillators. Now, Gupta, way back in 1950s, Gupta and Bleuler and many other our esteemed colleagues have taught us how to play with perturbative quantum gravity. So you are taking on a fixed background, small perturbation h b nu. You are not changing light cone structure or anything like that. You are taking these perturbations to be extremely, extremely tiny. And imagine that there is the energy momentum tensor of these two harmonic oscillators have certain momentum. And we know how to deal at least the gravity part. So gravity has a spin 2 component gamma mu nu and the spin 0 component gamma. We can expand it in terms of the basis pk and b mu nu k, and we can essentially quantize the graviton states. So both spin 2 and spin 0 components are relevant. So again, since you know the harmonic oscillator states, you know the graviton, very simple. You can talk about the interaction, which is governed by your universal Hamiltonian universal interaction. And so you can write down this interaction term. You can talk about one particle graviton state, because you're exciting gravitons in this process, as well as while it is interacting with your matter degrees of freedom. And you can compute the change in the gravitational energy due to the two harmonic oscillators. The only thing which you have to keep in mind, these harmonic oscillators are quantum in nature and the graviton is quantum. So essentially what you obtain when you compute this gravitational change in the gravitational energy, which is given by delta H G, is nothing but your operator valued Hamiltonian. And so this is the lowest order correction which you would get, including the momentum dependent terms. So you do recover your Newton's potential, but you also get momentum dependent contributions. And you can see that when you go into the center of mass frame, you recover the standard results of Zweiburn and Donoghue and many other colleagues who have already computed this kind of Hamiltonian. So since we know the state of the matter, these are harmonic oscillator states, I can put it in my Hamiltonian and just write the Hamiltonian now in terms of essentially creation and annihilation operator for the two systems of the harmonic oscillator states A and B. And then what I can do is that I can pick up all the interaction terms, which involves XA, XB, also the momentum PA and PB, and compute essentially my concurrence. Just to give you an example, I can also compute other witnesses as well, but just to give an example, let me compute the concurrence for just for 3 terms. You can do it for all other terms. Just to give you some example, I have computed here the concurrence for all the 3 terms. The one which involves purely the Newtonian potential is given in the shaded blue region, and then the momentum dependent terms are given in the green and the pinkish region. And in all the case, you can see that your concurrence is bigger than 0, and essentially all it tells you that since concurrence is bigger than 0, these two states of harmonic oscillators are entangled. So this is a very simple way to show how the local operation and quantum communication. Here, the quantum communication is done by none other than the spin 2 and spin 0 components of your graviton, leads to an entanglement of these two harmonic oscillator states. The question is how you're going to mimic this story, this part of the a very simple story into an experiment. And that's the place where the challenges come in. Because in experiment, when you want to do it, you cannot assume that gravity is the only term which is dominating. There's a huge background from every possible interaction, and the primary background comes in the electromagnetism. And I'll talk about how to even ameliorate some of these electromagnetic background as I give you the protocol to all of you. So this is known as the QGM protocol. So imagine what you're doing. So you're trying to mimic exactly the picture what I've shown you. Instead of harmonic oscillators, I'm trying to create the states in a Stern-Gerlach protocol. Stern-Gerlach is roughly the 100 years of Stern-Gerlach protocol, and everyone will recall what Stern-Gerlach did. The famous experiment where they put the electron in an inhomogeneous magnetic field, and on the screen you can see that the spins getting imprinted. So exactly you want to do the same experiment. So, but now because you're dealing with gravity, you have to assume some masses. So here, for the purpose of illustration, let's take system 1 and system 2. Let's embed a spin into this system, and I will come back how to do that. But take a neutral mass. So they become a very heavy hydrogen atom. The heavy hydrogen atom is because there is a spin, but the mass of this system is much heavier than your usual standard hydrogen atom. And with the help of Stern-Gerlach apparatus, you can create left and right states, as I've shown in for the system 1 and for system 2. And then you can talk about this gravitational interaction. This picture is exactly mimicking these pictures, or as a matter of fact, this picture of Alice and Bob. So one side you have got Alice's experiment, the other side you have got Bob's experiment. Now the experiment is nothing but the Stern-Gerlach experiment, which they are both performing. So what you do is that you allow it to evolve and do a one loop interference. And in the process, at the end of the day, you measure the spin of your system. So what was going to happen is that maybe 50-50, I mean, if it were purely classical, 50% you will get spin up, 50% you will get spin down. But if it's quantum, you will get the spin-spin correlation, which is not 50-50, but maybe 49-51 or something different from 50. So again, just for the purpose of illustration, I'm picking up only one term. Keep in mind that you can add momentum-dependent terms as well. And you should add momentum-dependent terms, but just to highlight that if you take the momentum, just the static potential, then you can compute the entanglement and the entanglement phase, which is essentially given by, because you have got 4 possibilities, up state, down state, and up, down, and down, up. So the entanglement will be there in the up, down, and down, up systems. And you can compute them. And again, so in a particular basis, you can compute this witness. So here I have chosen one particular basis, which I had shown you before. In this particular basis, if the trace of W rho is less than 0, you can show, or you can say that the two systems are entangled. And if the gravity is the only way to mediate, then the graviton is quantum in nature. However, in order to do this experiment, you require very, very challenging parameters. You require the masses. Just to give you an example, the masses have to be roughly 1 part in 10⁻⁴ kilogram. The superposition, Scotty, beam me up. For that, I need to create a superposition. And this superposition, we are talking about a very, very tiny mass still, 1 part in 10⁻⁴. But the superposition scale is also very tiny, 1 part in 10⁻⁴. But even then, it's extremely, extremely challenging. And the closest separation is roughly 200 micron. And I have to keep all these things running with a coherence time scale roughly at least roughly of 1 second. And I'll tell you why these parameters are important. Because what happens is that in a real life, of course, you need to take into account of various effects. You need to take into account decoherence. You need to take into account of coherence of your internal state of your system, external state of your system. So there are many things which you need to take into account, especially they're coming from the decoherence side. I'll tell you a little bit about what is the challenge of decoherence, but one of the things which is important here is the fact that you also have electromagnetic interactions. Because usually, if you take any system, so the way the system, now you can ask the question, what kind of system you're going to take? So usually right now, the current state of the art is that we would take a diamond, and usually naturally occurring diamond always comes with impurity. It may have carbon-14, it may have some nitrogen bonds as well. And especially if you have a nitrogen bond, then you can embed, because nitrogen has 14 and 12, so there is always a vacancy left. where you can embed an electron from outside, and it becomes like your heavy hydrogen atom. Because you're dealing with diamond, the density is very high. So essentially, these are heavy objects, and you can create them macroscopic superposition with essentially the hope is that you will create it with the help of very strong atom chip, which will generate a large gradient in magnetic field to push the two states apart and create a macroscopic superposition. You know the Hamiltonian for the diamond. You know what are the contributions, the spin magnetic field interaction. You know the diamagnetic contribution. All these parameters you know because you're dealing with the known physical system. So you take this Hamiltonian and you try to understand how to create a macroscopic superposition. However, this itself is a very interesting art. It is not easy. I will tell you what people have achieved so far. So what people have achieved, so this superposition which we were talking about here, the best current state of the art is done in Marcus Arndt's group in Zeilinger's, essentially in Zeilinger's group in Vienna. So far, people have taken a macroscopic system with a mass of roughly 10⁻⁻21 kilogram and created a very tiny spatial superposition. But what we are talking about here is at 8 or 9 orders of magnitude more than what people have achieved so far in a laboratory. So of course, there is a long way to go, but hope is that maybe we'll reach that goal maybe in, let's say in 5 years or 10 years time from now, if we work on these kind of systems. But having said so, there are many challenges. As I said, there are how do you prepare initial state? How do you neutralize your system? The system may have patch potentials or may have some defects that will give you some effects of decoherence, and I'll talk about that one such system later. But just to give you some idea, you see that you're dealing with a system like diamond kind of system. The internal vibration is mostly due to phonons. Those phonon vibrations I need to freeze. There could be other nucleus which is going to interfere with your spin system. So I need to even freeze those interactions. So the way to do it is to really go down. So you have to cool the system internally. You have to cool the system internally up to roughly even 0.1 Kelvin, so that no other degrees of freedom left other than your spin, which remains coherent for roughly 1 second. Not only that, you also require external cooling, because even if the system is heated, then it will emit black body radiation, or the black body radiation can hit the system and destroy the coherence, or there could be collisional decoherences. So you need to minimize that also. And again, you need to cool down the system externally, even below 1 Kelvin or so. So, and not only that, you have to create one of the best vacuum. As you know that one of the best vacuum is actually in the LHC, where the proton-proton beam is colliding. So there, the vacuum has been created by one of the best person is right now is Jerry Gabrielse, and his technology has helped to create the vacuum where you can talk about not even a single molecule or single atom is there inside the chamber. So that's the kind of vacuum you need. You can compute some of the decoherence rates. There are ways, it's nothing but a field theory approach to compute all these decoherence rate. Not only with static or not only with a fixed temperature, but in a time-dependent temperature change also, you can compute all these things, the decoherence rates. You need to know all the decoherence rates very well. And besides this, there are many challenges. So the challenges are immense in this game. But nevertheless, let me highlight one potential background, which is the biggest background for these kind of experiment, is the Casimir or dipole-dipole interaction. And you want that the gravitational interaction has to be at least larger than 10 times the Casimir interaction, so dipole-dipole interaction, which is being mediated by photon. So even this photon mediation will lead to an entanglement. So the question is, you need to go to a regime where at least you can trust your experiment. And this is exactly the regime which I was talking about here when I was giving you this number of 1 part in 10⁻⁴ kilogram, delta x is 10⁻⁻⁴ meters, and so on and so forth. So this is a parameter which makes sure that the gravitational induced entanglement is at least 10 times larger than your Casimir-Porte interaction. There are also ways to mitigate that. You can also put some kind of like a superconducting plate, so that your electromagnetic interactions cannot, the two systems cannot see electromagnetic interaction from each other, but the only thing is permeated is gravity. But however, there are walls as well, so you are embedding it in a chamber. So you have to think about all possible ways of mitigating the electromagnetic interactions. But just to highlight a number of problems. One of the biggest problems is actually gravity, because after all, the experiment is being done in a finite size box. So given a finite size box, you will always have relative acceleration or gravity gradient noise. And we are familiar with these kind of noises because even LIGO, Virgo, they also have to minimize this kind of relative acceleration and gravity gradient noises. So if Lake Geneva changes its width or height, essentially it's going to affect my experiment. If a butterfly passes by me, after, it will affect my experiment. So all these things will essentially affect this experiment by inducing a classical phase. And these classical phases, you can compute it, and you can ask what should be the exclusion zone. So you can talk about the exclusion zone, you can talk about the vacuum pressure. So just to highlight on the left-hand side, and these are the pressures, internal pressure and the external pressure you require of the capsule, and how heavy the capsule should be, what should be the length scale of the capsule. Everything goes into determining or minimizing the gravity gradient noise and relative acceleration noise. And the right-hand side, you can see that seismic noise is one of the biggest one. There are jerks, there are cars, there are planes, everything can actually cause disturbance for this experiment in terms of classical induced phase, which will destroy which will make it hard for us to dig out the real entangled phase. So one of the ways you can go is to, you require a dedicated lab where you go underground, because underground is good because your seismic noise is very low. That's why LIGO, even Virgo or Einstein telescope, they go underground, maybe 10 to 100 meters, underground. And then what you do is that you create a free fall laboratory. So the system is allowed to free fall. Sorry?
You have 5 minutes left.
Sure, thanks. I'm almost done, so thanks. So it's a free fall experiment you need to do. So essentially the two systems, they see only each other's gravity. There's no other gravity except this gravity gradient noise, which always be there. But the relative acceleration noise. But what you can do is that you can try to minimize this noise by having an embedded capsule kind of a system. So one capsule where the innermost capsule where you're performing the experiment is surrounded by another capsule, which is again very well encapsulated, in the sense it's a very well vacuum. So you have various levels of very, very good vacuum you create, and you try to create an embedded system, and you let it free fall, or you create some kind of like inverted pendulum technique, which is being used for LIGO's mirror or Virgo's mirror, because they are also a kind of like in a free fall mirror systems. So you need to bring this kind of technology to make sure that the innermost system is actually very much in a free fall kind of an environment where you're performing your experiment. Now, as I said, that maybe towards the end, in last 3-4 minutes, you can actually probe various different forms of gravity. It's not just Einstein's gravity. As you know, that this famous plot comes from the Adelberger's group in Seattle, and there are people they're looking into various kind of modifications of Einstein's gravity or via Yukawa kind of potential, and this is the plot, latest plot taken from 2020 data. And you can see that people have an extremely, it is a very nice plot. We have constrained this alpha parameter, which is coming in the Yukawa type of correction, and the length scale lambda, which tells you what are the regions which have been excluded. Of course, and nobody will tell me that modifications, say R square gravity or the Y square gravity, has to be as small as millimeter size distances it will appear. But nevertheless, you can keep your minds open, and you can still probe some of the new degrees of freedom, because the new degrees of freedom comes into your graviton propagator. If the graviton propagator is changed, your interaction changes, and that's going to be reflected in your entanglement phase as well. So one of the ways you can probe it is to look into time-dependent entanglement. So it's called entanglement tomography, something which we have recently realized. So what may happen is that certain interactions, such as even if there is a deficit charges on your system, maybe it's not completely neutral, but how you're going to do the experiment, and typically, usually this is the kind of system you are going to get in your laboratory. So then what can happen is that you can, if you know where the electromagnetic interactions are, the interaction will lead to, because you can compute the von Neumann entanglement entropy. And the von Neumann entanglement entropy, sometimes it has a sinusoidal or behavior. So if you can tune your parameter in such a way that you know exactly where the von Neumann entanglement entropy between the two systems vanishes, and if you can see anything above that, that will be a signal. So you can even constrain with this kind of system fairly strong bounds on this parameter alpha G and your length scale. And you see that in this plot, the dashed line, black line, and the solid black line are essentially coming from the data sets which Adelberger's group have achieved, Adelberger and other groups have achieved so far. So mostly this kind of experiment which are done in the laboratory are classical experiment, but since it's quantum, it can actually probe much, much deeper into the parameter space. As you can see, the alpha G can be probed all the way to 1 part in 10⁸ in roughly millimeter size separations. You can also probe non-perturbative aspects of gravity, because you can think about the loop quantum gravity, or maybe other formulations such as causal set dynamics, or maybe some non-local gravity. I think many people are very interested in this community present today. And you can, again, of course, it depends on the scale at which new physics comes in. And if there's no guarantee that the new physics will come in roughly at the 1 part in 10⁶ or 100 micron distances. But if it arises, you can actually distinguish the nature of gravity as well. And there are other ways you can probe. You can test the weak equivalence principle. You can test the idea of clocks in these kind of systems. So there are many different things you can do. Since my time is running out, so let me just stop my talk here, but by giving you a brief conclusion. So this is an experiment, as you can, hopefully I have given you in a picture that this is an experiment which requires many different branches of physics. You require material science, you require cooling, how to cool the systems. You're also testing certain foundations of quantum mechanics and quantum field theory. You're trying to even probe hidden sector physics, as I gave you an example of this kind of example. Now here you can also imagine that you can do something similar like Casimir or fifth force. Maybe there's axion mediated interaction. They will also lead to entanglement. So instead of I'm chasing gravity, but maybe at the end of the day, I found some parameter space for which, axion mediated interactions can also give rise to entanglement. So there are these kind of like, possibilities. The way you can distinguish all these things is only by doing recursive experiments, many experiments, and building statistics. So there are, you can test even certain people like Penrose, that talks about modification of quantum mechanics, and maybe the quantum mechanics gets nonlinear corrections, which can lead to collapse of your wave function. You can test some of these things. Certain modifications of this kind of physics can also test gravitational waves. And as I said, that you can test equivalence principle, and there are many things you can do. So with this, let me stop my talk, and let me thank all of you for attending. Thank you very much.
Yeah, thank you very much, Anupam, for this really nice talk. Are there questions? I see some questions on Zoom. First by Giorgio Torieri. Please go ahead.
Hello. So I think that this is sort of a great avenue of investigation, and you're tapping something that sort of was noticed by Matvei Bronstein in the first quantum gravity paper, which is one thing that I kind of think you're ignoring is that the entanglement between the detector and the system itself. I mean, these nanoparticles, if your Stern-Galois apparatus, your interferometer, whatever, if these things are light, when the nanoparticle passes through them, they will recoil. If these things are heavy, the gravitational interaction between the detector components and the nanoparticles will be bigger than the interaction between the nanoparticles. And the detector is a classical object, and the entanglement that you talked about in the introduction is a purely quantum entanglement. But the interaction is always partially classical and partially quantum, because you cannot eliminate the interaction between the detector components and the particles that you want to study. this is actually in the original paper of Matvei Bronstein about how to quantize gravity. He actually makes this point that one of the assumptions we have about quantization is that the charge over mass has to be vanishing, because otherwise you have back reaction between the system and the detector, and in gravity it's impossible to avoid that. So how would you avoid the detector components interacting with the system and sort of spoiling the quantum coherence?
Okay, it's a very good question. So what is happening, maybe let me reiterate. So your Stern-Gerlach is created by, so essentially think about this atom chip, and the currents are flowing here. And these currents are responsible to create inhomogeneous magnetic field. And the way you are creating a superposition is with the help of this magnetic field. So the magnetic field and the current, you have to know very, very precisely. If you don't know very precisely, then you are absolutely correct. It will lead to decoher the system. You cannot even do the experiment. So you have to know this so precisely that even just a single electron passing through your certain cross section per second, you have to know it extremely precise. If you do not, this will exactly what you said, that it will back react in your geometry. It will not even create your superposition. So it is absolutely a good question, and it requires huge challenges to make sure that you can create your superposition, and you need to know all these parameters. You need to really do the perturbations. There's a very famous paper by Schwinger and his company, Martin Scully. They have already pointed this out, that even in Stern-Gerlach it's extremely hard to do one loop effects. But recently, actually, we have shown with some of our colleagues in Israel that not very heavy system, like 100 rubidium. So 10⁻⁻27 times 100 10⁻⁻25 kilogram system, they have created a macroscopic superposition. Of course, this is nowhere close to testing quantum nature of gravity, but these are the very first steps which you can take in order to create this Stern-Gerlach apparatus. So now your second part of your question is that how are you going to disentangle the Stern-Gerlach system with respect to the graviton system? So it's the only thing which I would suggest is that you have to look into many runs. So you, of course, with one run you cannot do the experiment. You need to build statistics. And you need to go into Fisher information techniques and various other techniques to, typically you would do this experiment at least 1 billion times to build enough statistics. Because if you think about this, one experiment will be done, say a couple of seconds, let's say 5 seconds, and to build enough statistics, you really need to run it continuously for more than a year or so, and then you do this kind of analysis. But yeah, your question is absolutely right, that you have to find ways how to really disentangle all these effects. These are part of your systematics, indeed.
Just as a comment, I mean, it's not just a question of numerical precision. Your particle, whatever it is, recoils with, say, the magnet. And this recoil is sort of part of the interaction.
That's true. That's
if you reach that precision, that recoil is part, or it isn't if the magnet is very heavy. But if the magnet is very heavy, it gravitates as well.
Yeah, so essentially all these systems are hinged, and everything is in a free fall. So the way you have to think of it, imagine that everything is hinged and you let it free fall. And of course, the current which is going through, you have to make sure that they are, very, very, fine-tuned. You know exactly what you're talking about. Otherwise, you're absolutely correct. You may see some, one of the things which you can even have is that current will give you entanglement between the two Stern-Gerlach system, but then these are part of your background, and you should know your background extremely well to see any of these, to get rid of these backgrounds. You need to do, you may have to keep another interferometer to even see what is your background and how much all these disturbances are causing you. So, these are absolutely wonderful questions.
Here's another question by Philip Mannheim. Please go ahead.
Yes, good morning, Anupam. Nice to meet up with you. again. And oh, by the way, and hello, Giorgio. What I wanted to ask are 3 points. Point number one, you gave a formula by Donahue and Holstein and Bose and so on. But there was no sign of H bar in it. Had you just suppressed it, or is it not there?
You see that no, the lowest order interaction term which we see doesn't have H bar. But we know that these interactions are being caused by exchange of your graviton.
So that formula itself, if you test it and you find something, it doesn't really tell you that gravity knows about H bar.
No, the H bar is always there. It's just in the tree level, they cancel out. But that doesn't mean that the gravity, I mean, is...
I agree on that. But therefore, the tree approximation graph will not tell you anything about quantum gravity. By the way, it's the same thing with the Coulomb potential. The Born approximation to Coulomb.
No, that is absolutely wrong. People have seen entanglement. No, this is absolutely wrong. Who said that? I mean, the entire quantum computing is based on either your phonon mediated, entanglement or photon induced entanglement. And people have seen this experiment. These are regular experiments being done in the laboratory. So who said that Coulomb interaction is not responsible for entangling? And who says that the photon is not a quantum system?
Oh, no, I didn't say that. I just said
so
the Born approximation to Coulomb is independent of H bar.
Yeah,
that was all I said. I didn't say that there were no other effects.
That's true. I agree that the H bar eventually it cancels out, but that doesn't mean that the photon is not quantum. Photon is highly quantum system.
Okay, that was the first question. The second question is, you may have just gone too quickly for me. How did you screen out entanglement due to anything other than gravity?
That is a wonderful question, yes. And these are the challenges. Absolutely. I agree that these are the immense challenges. So one of the things is that this, as I said, the electromagnetic interaction will cause a huge background. And especially the Casimir dipole-dipole interaction. So let me just show you that part. So yes, you need to worry these kind of backgrounds. And so just to give an example, so I had to go to a regime where the gravity-induced entanglement is at least 10 times bigger than the Casimir-Podler or dipole-dipole interaction. And for that reason, actually, I had to go for a very heavy system, which is 1 part in 10⁻14 kilogram. But these are very, very difficult, challenges. Yes. So I absolutely agree that known physics is the biggest challenge. And these are the ways. I mean, there are ways you can mitigate it.
Well, I think that if you look at things objectively, which funding agencies don't, you can probably get around these kind of problems at less than the cost of LIGO.
That's true. That's true. That's true. But still, it's a big challenge. Right now, the way the war is going on, and I spoke to the spokesperson of Einstein telescope, which is going to be hopefully built in Netherlands, Germany, and Belgium. They're saying every day the war is costing them science money. So we'll see how it goes.
By the way, Boston University's photonics lab is right next to the Massachusetts Turnpike. But they have managed to find screening mechanisms to stabilize their experiments.
No, that's true. Yeah, very nice. Yeah.
Okay, and then my third comment is, if you do see an effect, and it is finite, which it would have to be if you saw it, it would mean that radiative corrections to gravity cannot be infinite. It doesn't tell you what the theory of gravity is, but it would tell you what the theory of gravity isn't.
That's true. No, you are correct. Absolutely correct. Yeah, I agree. Absolutely. Yeah, it's a very interesting and important point. Thanks for making this. Yeah.
Okay, are there any last minute questions? I don't see any on Zoom and also not here. So let's thank Anupam and all the other speakers of the morning again.